Welcome to today's lesson. You are on Unit 3 Curve Sketching, Lesson 6, Optimization. So in this lesson, you will be learning a variety of real-life problems in which it is necessary to find the best or optimal value. And we're going to do this using calculus. I have included in this section a page in which lists a variety of tools or steps that you can use to better help you solve these type of problems. They can get a little bit tricky. We will come up with a few problem-solving steps of our own. However, they do require a little bit of critical thinking, so don't be discouraged if they are a little bit challenging. So example number 1, a lifeguard had 200 meters of rope and some buoys with which she intends to enclose a rectangular area at a lake for swimming. The beach will form one side of the rectangle, with the rope forming the other three sides. Find the dimensions that will produce the maximum enclosed area if A, there are no restrictions on the dimensions, B, due to the depth of the water, the area cannot exceed more than 40 meters into the lake. So I know you've seen these questions before. Perhaps you used quadratics in order to solve them. What we're going to do today is look at using calculus in order to solve these type of optimization questions. So the first thing that I always do in solving these questions is draw a diagram. Okay, so what we were told is that the beach, was going to form one side of the fence, okay, and then we have a rope that is going to form the other three sides. Okay, here we are. Okay, so this here is all water, okay, and this is the beach. Okay, so we'll just give the sides some variables. We have this is length, okay, and this will be our width. And we want to, so always try and figure out what we're trying to maximize. We want to maximize the area. We want to maximize the area. So let's come up with an equation that's going to relate these variables with area. So we know the area is equal to length times width. Okay, length times width. What else do we know? Well, we're also given 200 meters. We're also given 200 meters of rope. Okay, so that means that we have the perimeter. So the perimeter is equal to, in this case, we only have 2 lengths and 1 width. So we have perimeter is equal to 2 lengths plus 1 width. But we know that the perimeter is equal to 200. So we can just simply replace P with 200. Okay, so now we have two equations that are going to help us. And we always want to try to eliminate one of the variables. Okay, so again, we're going to use the area and we're going to maximize that, but we have two variables. So we have another equation in which we can try to isolate one of these variables to eliminate the other. In this case, looking at this final equation here, I would try and isolate for W, eliminate it because it looks like the more simple variable to isolate. So just moving this around, I'm just going to flip the entire equation around. So what it's going to look like is W is then equal to 200 minus 2L. Okay. So now I'm going to take this and I'm going to sub it into the area. So area then is equal to L times 200 minus 2L. Okay. And just expanding that, what I will have now is 200L minus 2L squared. Okay. So I want to maximize the area. When I want to find the maximum of something, what do? Well, what I'm actually doing is finding the critical point. Okay, so when I want to find the maximum, I'm actually finding, okay, in this case, A now is a function of L. Okay, so A prime at L is then equal to 0. So I'm actually trying to find the critical point. So I want to take the first derivative, this is my function, of the area with respect to L. So let's do that. A primed at L then is equal to 200 minus 4L. Okay. To find the maximum, I want to set the derivative equal to 0. So this is always your goal, okay, is to take the first derivative, come up with two equations, eliminate one of the variables, okay. Then you have a function with respect to the other variable, find the derivative and set it equal to 0. Those are always the steps. So now I want to isolate for L. So 4L, just moving it to the other side, is equal to 200. L then is equal to 50. Okay, so my length that will give me the maximum area is 50. Okay, knowing that it's 50, now I need to find also the width. Am I asked for width? Yes, I am asked for width because I want the dimension. So I can take that length and I can sub it right back into my perimeter. Okay, so my perimeter equation, I have 200. So what I'm doing now is subbing back into 200 is equal to 50 times 2 plus width. So then my width is equal to 100. Okay, so therefore the dimensions for the maximum area is 50 by 100. And I think we are dealing in meters. Okay, meters. 50 meters by 100 meters. And if we wanted to just multiply those, where the maximum area is then 5,000 meters squared if we really wanted to complete it. So the maximum area is then 5,000 meters squared. Okay, so part B, now what we have is restrictions. Okay, we have restrictions on the length, in which the length, what we're saying now is that the length is in between 0 and 40. So it cannot exceed 40, but it can also not be negative. Okay. So what we need to do now is to take the length is equal to 40, which is one of the endpoints of our function. So it's the endpoint of our function. If you really wanted to see what this looks like, it's going to be a parabola, okay, is our derivative. So we want to take a look at the endpoint. So if this was 50, 40 is going to be somewhere over here, okay? So let's determine the area. So first, let's take the length and we plug it back into the perimeter equation so that we can find out what the width is. So we're working this out. Our width then is equal to, okay, moving this around, so that would work out to be 80, so width is then equal to 120 meters, okay, meters. So to find the area then we're just going to say 40 times 120, which is equal to 4,800 meters squared. So that's going to be our maximum area if we had restrictions in which the length cannot exceed 40. In this case, that would be our maximum area because we can see that when we found 50, 50 was our true maximum without restrictions. And there's going to be no other value that's going to, where the area is going to exceed that. Okay. Okay. So therefore, the max area of 4,800 meters squared occurs when the dimensions are 40 meters by 120 meters. Let's look at example number 2. I love these questions, I'll be honest. I'm a nerd that way. I really like them. I think they're great. So let's read number 2. A cardboard box with a square base is to have a volume of 8 liters. Find the dimensions that will minimize the amount of cardboard to be used. B, the cardboard for the box costs 0.1 cents per centimeter squared, but the cardboard for the bottom is thicker, so it costs 3 times as much. Find the dimensions that will minimize the cost of the cardboard. Okay, so let's focus on question 2A first. Okay, so it looks like we're going to have to do a little bit of conversion here, because you'll notice that we are dealing in liters as well as in centimeters squared. So we know that one liter is also equal to 1,000 centimeters cubed. Okay, so we need to convert. So we're given that we have 8 liters. So we have 8 liters, and then we have 8,000 meters cubed. Okay, so first things first, let's draw the diagram. We were given a diagram, but that's okay. I'm just going to redraw it for us. So here we are. I'm not an artist, so I'll do my best. Let's do that. And that. That's not too bad anyway. Okay, so here's our height. Here's x. We don't really know what this box or this bottom part, we're told that it's square, so that means that this length is also the same as the width. Okay, that's all we know. We know the height is different. Okay, so we want to find the dimensions that will minimize the amount of cardboard to be used. So the amount of cardboard in geometry would relate back to surface area. Okay, so this is something that you're going to need to look up. On the exam, you will be given these formulas if you do need them. There will be a formula sheet, so you will not have to memorize, go back to grade 9 and take those sheets that you got for EQAO and try and memorize all those formulas. They will be given to you. In this case, we can actually come up with the surface area ourselves, even though we don't know the equation. We have enough knowledge just basically from this. Okay, so in first case here, what I would do is the surface area is equal to, okay, so we know that the bottom, the 2 on either end, so here, then the bottom piece is going to be the same. Okay, so the area for the bottom piece, so this and this, would be x squared. Okay, so we're going to have 2 of them. Then we have 4 sides that go all the way around. So we're going to go 4 plus 4, which then this, if you're just looking at this surface right here, okay, it's height times x. So x, h. Okay, so that's our surface area. Just simplifying a little bit more, so 2x squared plus 4x, 4xh. Okay, so that's our one equation. We need another equation because we have too many variables here. Well, let's see, we're given the volume, okay, and we've converted the volume now to meters. That should be centimeters cubed. Okay, I'm just going to rewrite that as 8,000 centimeters cubed. Okay, so how can we find the volume? Maybe we can relate this somehow. So we can say volume is equal to length times width times height. So x squared times the height. Okay, we know the volume is 8,000 in the proper units. X squared h. Okay. What's easier to isolate? I'm going to say h. I like h in this case. I really don't want to take any square roots, so I'm just going to leave that one alone. Okay, let's take this now and plug it into our surface area. So surface area then is equal to 2x squared plus 4x 8,000 over x squared. Okay, so one of these will cancel with one of those. X squared plus, now 4 times 8,000 is 32,000. Okay, and then I have an x in the denominator, but I'm going to go ahead and bring that to the numerator, and you'll see why. So now I have surface area as a function of x. Okay. Okay, so I want to minimize the amount of cardboard. So I want to minimize the surface area. So what I'm looking for is this. That. Okay, so take the derivative. 4x minus 3,200. 32,000, my goodness. Negative 2. Okay, and I'm going to set that equal to 0. What can I do here? Well, I can factor out a 4. And that's about it. But I don't know if I need to yet. So let's just carry on. And I don't think I need to. Okay, so what I'm going to do is move this over here. Okay, so yeah, we'll move this over here. Let's see, will that help us at all? Yeah, sure. Let's try it. 3,200 all over x squared is equal to 4x. Okay, so I'm going to multiply the x squared to 4x, 3,200, and I'm going to divide both sides by 4. Okay, so I'm just going to swap them really. So x cubed. Okay, so this turns into 8,000. So x cubed is equal to 8,000. That means x is equal to 200. Okay, so 200 centimeters. Whoops, I think I've got one too many zeros, so 20 centimeters. Okay, so if we have x is equal to 20, so we have the length and the width. Let's find the height. Plug it right back into here. So then the height then is equal to 8,000 20 squared 8,000 divided by 400 is equal to 20 centimeters. So, surprise, surprise, we have a cube. Okay. Yes, the optimal shape, as long as there's no restriction, is always going to be a cube, okay, or a square. Okay, now what? B. Well, I wanted to click back to this part of the question so that you can read it again. The cardboard for the box costs 0.1 centimeters, or cents per centimeter squared, but the cardboard for the bottom is thicker, okay, so it costs 3 times as much. Find the dimensions that will minimize the cost of the cardboard. So in this case now we're going to weight each part of the box a separate or a different weighting, and then we're going to then take the derivative of that in order to minimize what we're going to be calling the cost function. Okay, so again, let's just write out the surface area relation here, surface area formula that we came up with for our box after we made our substitution and our cancellations and simplifications. That's the word I'm looking for. Okay, so there's our surface area, but we're going to weight each part of the cardboard box a different weighting. Okay, so we're going to call this now the cost function. There's the cost function. Okay, so remember the box the tops are just squares, okay? Top and the bottom. So one of the sides, I think it said that it was the bottom, was it not? The bottom was thicker. Okay. The bottom was thicker. So if the bottom was thicker, we'll say that that's 0.3 x squared, and everything else will be 0.1 weighting. 32,000 over x. Okay. Now let's simplify that a little bit. 0.4 x squared plus 3,200 over x. Okay. Now, let's see. I'm going to change that. Okay, so I'm going to change this just so that it'll make it easier for us to differentiate or to derive, which is another way of saying differentiate. Okay, so you might hear me using that term as well by calling it derive. And remember, I want to minimize. So what I'm looking for is this. Okay, so find the derivative of the cost function. 0.8x minus 3,200 x to the negative 2, okay? And then, I've eliminated that. Okay, perfect. So we're going to say that 0 is equal to 0.8x minus 3,200 all over x squared. Okay, so we're going to do the same thing as before, in which we move this to the other side and isolate for x. So 3,200 over x squared is equal to 0.8x. Okay, flip-flop x cubed. Okay, that works out to be x cubed is then equal to 4,000. Okay, and then punching that into our calculator, we would see it's approximately equal to 15.9 centimeters. Okay, so that's our x. Let's now put it back into our height. And we said the height was equal to 8,000 over x squared. Okay, so height then would be equal to 8,000 over 15.9 squared. Okay, and now punching that into our calculator, the height then is equal to around 31.7 centimeters. Okay, so therefore the dimensions of the box that will minimize the cost is 15.9 centimeters by 15.9 centimeters. I think I forgot the second side there, or one of the lengths or widths in the last solution, 31.7 centimeters. Okay, that's a 31. Okay, and that sums it up.